Okay, hi everyone. Welcome to the Graphs and Matroids seminar. Today we've got Bertrand Guenin from University of Waterloo presenting on graphs with the same even cycles. Bertrand.
Well, thank you for the introduction. So many years ago, I was looking at the class of matroid called even cycle matroid. And as a side problem, we were interested in sine graphs that have the same same set of even cycles. And I looked at this problem with various people over the years, and every time we looked at it, it seemed like the answer was getting messier and messier. And what I want to convince you today is that maybe there's a very clean answer to this problem after all. So this is joint work with a number of different co-workers. So Zuhair Furshu was an undergrad research assistant. Chelwan Heo is a current PhD student who's going to graduate in a couple of months. And Irene Pivoto is a former PhD student of mine. So let's use our time machine and go back to the 1930s. And Whitney asked the following question. So if I give you two graphs, when is it that two graphs have the same cycles? So I should be explicit what I mean by the same cycles. So first, we're looking at edge-labeled graphs. And a cycle for us is going to be a subset of the edges that induces an Eulerian subgraph. So I've given two examples here. So here on the left, you have those wiggly edges there, which correspond to the set 1, 2, 3, 4, 5. And if I look at the graph which is induced by those edges there, they would have degree 2. And if I look at this set on the right, the graph induced by the wiggly edges would have degree 2 or 4, right? So those are two examples of cycles. And if I look at the set of all cycles of a graph G, which I'll denote by cycle G, is just a binary vector space. So my apologies to matroid theorists. The entire talk is going to be in the language of graphs. All right, so I'll rephrase the question here, right? So suppose that you have two graphs and cycle of G1 is cycle of G2. So they have the same set of cycles. What is the relationship between G1 and G2? So one way to think of this question is to think of operations that will preserve cycles. So one operation is you just take two different components of your graph, and then you just identify one vertex. And of course, you could do the reverse operation as well. And we call that a one flip, and it's very easy to see that this is going to preserve cycles. You can do a slightly more complicated operation where you look at a vertex separation with two vertices on the boundary. You separate the graph along that those two vertices here, and then you just flip part of the graph and then just glue it back together, right? So I flipped the green path apart in this example here. And again, it's easy to see that two flips will preserve the set of cycles. So you could ask, well, can I do anything else? And the answer is no. And this is what Whitney proved, right? So two graphs have the same set of cycles if and only if they are related by a sequence of one flips and two flips. So I'm going to say that two graphs are equivalent if I can go from one to the other by doing one flips and two flips. Right, so this is Whitney's theorem there. Now this is a nice theorem. In particular, it tells you that if a graph is free connected and any other graph has the same set of cycles, then those two graphs have to be the same. All right, so we had a statement in terms of cycle. Of course, I can have a statement in terms of cut, which will prove useful later on. So I'm going to use the following notation. Cut G is going to be the set of all cuts of a graph G. And again, it's going to be a binary vector space. And I could ask, well, when is it that two graphs have the same cuts? Well, it's the same thing as asking if two graphs have the same set of cycles, because cycles and cut are just orthogonal subspaces, right? So a more general way of stating Witten's theorem is to say that you have three equivalent statements. Two graphs have the same set of cycles is equivalent to saying that two graphs have the same set of cuts, which is equivalent to saying that two graphs are related by a sequence of one flips or two flips, or what are called equivalent. All right, so now let's crank up a slightly more modern time machine and go to 1982. And I want to talk about a less well-known result by Xi. So Xi is a former grad student of Neil Robertson, and he looked at a question which is very similar to what Whitney investigated. So I have two graphs, G1 and G2, and now I'm telling you that the cycles of the first graph, G1, is contained in the set of cycles of the graph G2, and moreover, they have codimension 1, meaning that the dimension of the cycle space of G1 is equal to the dimension of the cycle space of G2 minus 1. Right, so this is a setup very similar to the setup that Whitney investigated, and you want to know the relationship between G1 and G2. So let's try to look at some example, right? So if I ask you to build up an example, you'd probably come up with the following construction. So you start with a graph G1, say a connected graph, and then you pick an arbitrary pair of vertices, say U and V. And then you're just going to identify those two vertices here, right? So when you do this, clearly every cycle of G1 is going to be a cycle of G2, right? But actually you get a strict inclusion because, well, any UV pass in G1 is turning now into a cycle of G2, right? So you get strict inclusion. And in fact, if you remember the formula for computing the dimension of a cycle space, you'll realize because G2 has one fewer vertex than G1, it satisfies the second condition here. The dimension differs just by exactly 1. So this is a very natural construction. It's probably the first construction you would come up with if you wanted to investigate the class of graphs that has this relationship. But there are things which are more surprising. So you can do a construction that looks something like this, and I haven't completely described it, but you start off with a wheel, and then you just fill up every little triangle in your wheel by some arbitrary graph. Then essentially you can reshuffle every one of those little triangles there to get a structure like G2. And you can do this with an arbitrary number of pieces, right? And now the exact details of how to do the reshuffling is not very important, but the point is that this is a very well structured construction. It's a very precise construction, and it's probably not the construction you would think of at first hand. It's a little surprising. Now, can you do anything else? You can do one more construction, and it has a little bit of the same flavor as the previous construction. So every triangle blue here represents an arbitrary graph, and you can see that those little triangles there share 4 vertices. So I have a green line here which indicate that those vertices are the same. So on the left, you're somehow stacking up those triangles on 4 special vertices, and on the right, you're stacking up those triangles on 3 special vertices, right? And you have to rearrange it in the right way. There's a rule for that. But again, you're going to get a pair of graphs that are satisfying this condition. The cycle space of the first graph will be contained in the cycle space of the second graph, and the dimension will differ exactly by 1. And can you do anything else? And the answer is no. And this is what Xi proved. So again, I'm adding here the condition that G1 and G2 are 3 connected. And again, I have this condition about cycle space of G1 being contained in the cycle space of G2, and the difference in the dimension being 1. And then G1 and G2 has to be one of the construction I've shown you, right? So obtained by identifying two vertices, or this wheel type construction, or the last construction, which we just call a widget pair, right? Now, we have this condition that the graphs have to be free connected, but you don't really need it. But then the statement becomes a little uglier, but you can just allow one flips and two flips. So this is a very pretty result. That result got sort of forgotten about, at least we didn't know about it until I think Irene Pivotto asked Neil Robertson. He said, yeah, I had a student who did this in the 80s. She went to work on Wall Street, and the result was never published anywhere. So a few years ago, Zuhair Furshu was an undergrad research assistant, and we wrote a more accessible proof of this result, and it appeared in Combinatorica last year. All right, so this is a statement about cycle space. And of course, you can do a statement about cuts as well, right? Because, well, I can just have cycles of G1 containing cycle of G2. So if I look at the cut space, I'll just reverse the inclusion, right? So you just get this particular statement here, right? So this is Schi's theorem for cut spaces. All right, so now we have somehow those two conditions here, right? So we looked at cycle of G1 containing cycle of G2, and the dimension differ by 1, or the cut of G1 contains the cut of G2, and again, the dimension differs by 1. They're not very sort of natural condition to look at. So I'd like to rephrase this condition in terms of cycles in a condition that involve sine graphs. And I'd like to restate this condition on cuts in terms of graphs, right? So I need to tell you, to remind you of what a sine graph is, right? So a sine graph is just a pair, where the first element in a pair is a graph, and the second element in a pair is a subset of the edges that we call the signature. And the reason we care about sine graphs in this lecture is because we care about even cycle. So we're going to say that a cycle is even if it intersects the signature with even parity, right? So the wiggly edges here are form a cycle here. The red edges form my signature. I have two red edges, so two edges in the signature in that cycle there, so that cycle is even, right? And here you get union of those two triangles there, that forms a cycle, that's an Eulerian subgraph, and you get one edge from the signature here and one edge from the signature here, so the union of those two triangles there is again an even cycle. And again, the set of all even cycle is binary vector space. Every time I say binary vector space, you can substitute binary matroid if you want to, makes you happier. All right, and one last definition. I'm going to say that a sine graph is bipartite if every cycle is even, right? And you'll see why I care about this condition in a second. All right, so let's just look at the condition that we investigated. So this condition here on top, right, was the condition that was characterized by Schi. I claim that this is equivalent to the following statement. So I can find a set sigma, so a subset of the edges of G2, right? So that the even cycle of G2 sigma is equal to the cycle of G1, and G2 sigma is not bipartite, right? So let's just look at the second statement and convince ourselves that it implies the first statement, right? Every cycle of G1 is an even cycle of G2 sigma, right? So in particular, it's a cycle of G2. So I certainly have the condition that cycle of G1 is is a subset of cycle of G2, right? And you notice that I need to impose that G2 sigma is not bipartite, because otherwise the even cycle of G2 sigma would just be the set of all cycles, right? And I wouldn't have a proper inclusion here, right? And then you can convince yourself that the difference in a dimension can be at most 1. And so it implies that this second statement here is implies the first statement. In fact, those two statements are equivalent. So one way you can think of this is that Shea's theorem is telling you something about the relationship between a graph and a sine graph, where the cycle of the graph is equal to the even cycle of the sine graph, right? Shea's theorem is going to characterize that. In fact, you have no choice for the signature. The signature is going to be unique up to resigning. We'll talk about resigning later. Okay, so I want to do now the same thing, but for the second condition. So we had a version of Shea's theorem in terms of cuts, and I want to restate that condition, but in terms of grafts, right? So what is a graft? A graft is going to be a pair where I have the graph G, and I have T, which is a subset of the terminal, and I'm going to impose that T has to have even cardinality, and you'll see why in a second. Then I can define the notion of an even cut. So I have a cut delta U. U is the shore, one of the shores of my cut. And my cut is going to be even if I have an even number of terminals on each of the shores, right? And for this to be well defined, of course, I needed to have an even number of terminals in the graft, right? So I have the same parity on both shores, right? Right, so those wiggly edges here form an even cut. The square red vertices are my terminals. So I would have two terminals in U. This is my set U here, and two terminals outside U. And I could have those wiggly edges here as well, where one of the shores just contains two terminals here. And I need to have, again, that definition here, which is another notion. Oh, I need to have a notation. So the set of all even cuts of a graft is denoted by E cut of GT. And again, it's a binary vector space. And I'm going to say that a graft is Eulerian if every cut is even, right? So this is the analog of bipartiteness, but it's for the cuts. Right? And so why did I need that? Well, because I want to restate this condition here, right? So this is the cut. This is a hypothesis for the cut version of Shea's theorem. So the cut of G1 contains the cuts of G2, and the difference in dimension for the cut space is just 1. And that's equivalent to saying that I can find a set of terminals for G1 so that the even cuts of G1T is equal to the cut of G2. And I need to have the condition that G1T is not Eulerian. And again, you need that because if it was Eulerian, then every even cut of G1T would just be just a set of all cuts. And so we'd have that cut of G1 is cut of G2. Right. Right. And again, if I give you two grafts, right? So I give you one graph and I give you one graph, and I tell you that the even cut in the graft is equal to the cut in the graph, right? Then I know exactly what the relationship is between the graft and the graph through Shea's theorem, right? In fact, in this case, I have no choice for T. There's a unique T that's going to work. All right, so before I move further, I want to just give you just a glimpse of the argument for proving Shea's theorem, just a sort of high level view. The basic idea is to essentially reduce the problem to witness theorem, right? So witness theorem characterizes a relationship between two graphs when they have the same set of cycles, or equivalently when they have the same set of cuts. So what you do is you try to prove Schi's theorem. You use a version that involves cuts, right? So you should say that the even cuts of the graph G1T is equal to the cuts of G2, right? And then you pick one terminal here, right? And then you just remove all the edges of A, right? So that's what I've written here, right? I think of this as a set. I have a set of even cuts of G1T, which is a set of all cuts of G2, right? And then I just remove the set A from each of those families of sets, right? Now, if I look at G2, if I delete all the edges in A, right? Well, I just get all the cuts of G deleted A, right? Now here, this looks a little more complicated because I'm looking at even cuts. But what happens is that I'm deleting all the edges which are incident to a terminal. So I'm really turning all the even cuts into cuts as well, right? And so now what I've done is that I've turned, I started from G1 and G2, and now I'm looking at cuts of G1 deleted A's, cuts of G2 deleted A, and now I know that they are equivalent, right? So somehow after removing a small number of edges, right, then the two graphs becomes equivalent, right? So you can see somehow why, the only sort of highly connected instance is the one which corresponds to the pinch instance, right? If you think a little bit, that's where it comes from. All right, so now I want to move on to sort of generalization of Schi's theorem. And there's going to be two questions, one which involves cuts and one which involves cycles. But we'll see that those two questions turn out to be the same. All right, so the question about sine graph is the following. So I give you two sine graphs, G1 sigma 1, G2 sigma 2. And I tell you that those two sine graphs have the same even cycles. And I'd like to understand what is the relationship between those two sine graphs. So here's an example. So it looks like the same graph, but they edge label graphs. So if you look at what happens here is that I've turned some triangles into matchings. So the labeling has gone wonky when I went from G1 sigma 1 to G2 sigma 2. But I was able to do that preserving even cycles. So that looks a bit of a nasty example. Anyway, let's leave that aside. That example will come back. Let's look at even cuts. So I take two graphs now, so G1 and a set of terminals T1, G2 and a set of terminals T2. And I'm asking you telling you that they have the same even cuts, and I would like to know what is the relationship between those two graphs. So let's look at an example. It looks a little familiar, except now those square vertices are the terminals. So I got 6 terminals here, and I have 6 terminals here. And if you check, those two graphs have the same even cuts. So that graph here comes up again. And again, you have a somewhat nasty example for two graphs that have the same even cuts. All right, so those were the two questions. And well, you already noticed that I gave you somehow the same example twice, right? Except for the first example, I gave a signature, and the second example, I gave a bunch of terminals. But the underlying pair of graphs was the same. And in fact, this is no accident. The two questions are equivalent. So I'm going to show you why they're equivalent. So let me just point out that I'm going to assume that those two graphs, G1 and G2, are inequivalent. So if the two graphs are related by one flip and two flip, then we can just use witness theorem to understand the relationship between G1 and G2, and then the relationship between sigma 1 and sigma 2 is also straightforward. right? So here's a theorem that we proved a long time ago. So I give you a pair of inequivalent graphs, G1 and G2. So those are two graphs with edge labels, and think of the edge labels as being the same on both graphs. Then I tell you that you can find a pair of signatures so that the two sine graph would have the same even cycles. If and only if you can find a pair of terminals so that the corresponding even cuts, graphs would have the same even cuts, right? So somehow it tells you that those two problems come in pair, right? So here's a little example here. So what I've done is, here's a pair of graphs here, right? And I've indicated both the signature and the terminal on those pairs of graphs there. So the red edges are the odd edges, so sigma 1 on the left, sigma 2 on the right. And the square vertices are T1 on the left and T2 on the right. And you can see that I was able to do both things at the same time, right? And this is what the theorem tells you. Now, of course, not every pair of graphs with the same edge labels will do, right? But some of them will. And if you can do it with the signatures, you can do it with the terminals. So we're going to call pairs of graphs that admit one of those pairs of signatures or one of those pairs of terminals. We'll just call them siblings, right? So let me just restate that, that definition, because that's going to be the important definition here. So I take a pair of inequivalent graphs, right, for which there exists a pair of signatures so that the even cycles are the same, or equivalently for which there exists a pair of terminal for which the even cuts are the same, right? So that's what we call siblings. And then the two questions which I mentioned before really boil down to understanding siblings, right? Well, you could say, well, what happens? I still need to figure out what choices I can do for sigma 1 and sigma 2, and what choices I can do for T1 and T2. But it turns out that essentially those are determined by the graph G1 and G2. So if you know the relationship between the graph G1 and G2, you also know what sigma 1 and sigma 2 are up to resigning, right? In fact, we'll just say that sigma 1, sigma 2 is a matching signature pair, right? Because that pair is determined by G1 and G2, and we'll say that T1 and T2 is a matching terminal pair. So for the rest of the talk, I'm going to look at the problem of characterizing siblings, right? This is going to be my goal. So what is a class of siblings that we understand? Well, we understand the ones which arrive from Shea's theorem, right? So if I have G1, G2 which are siblings, and I tell you that there's a graph H such that the cycle of H is equal to the even cycle of G1 sigma 1, or equivalently the even cycle of G2 sigma 2, right? Then Shea's theorem is going to tell you the relationship between H and G1. Then it's also going to tell you the relationship between H and G2. So indirectly, it tells you the relationship between G1 and G2. Right? So if I have this first situation here, then I'm sort of happy. Shea's theorem is giving me a precise enough characterization of the relationship between G1 and G2. And similarly, you could use the cut version of Shea's theorem, right, which is telling you something different. And if the even cuts of G1, T1 is equal to the cut of some graph H, then I know the relationship between G1 and H, and I know the relationship between G2 and H, right? Now, I want to point out that this is not an and statement, right? The two things don't happen at the same time. So sometimes when you use a cycle version of Shea's theorem, you get some information, and sometimes when you use the cut version of Shea's theorem, you get some information. Right? So those are really two basic classes. You have a cycle version and a cut version of Shea's siblings, right? All right. So again, let me just sort of summarize where we are. So we have this notion of siblings. So this is just a pair of graphs for which I can find signatures so that we have the same even cycles. And equivalently, I can find a pair of terminals so that I have the same even cut. And a well understood class of siblings are the ones which are explained by Schi's theorem. So I'm going to essentially exclude those. I'll assume that they are part of my basic class. All right, so let's look at examples of siblings, and I'm going to give you examples of siblings which are not Schi siblings, because we already know those. So this is the K6 example that you've seen before, right? Here's a nice example. I can give a talk at CNO without giving the Peterson somewhere. And again, it looks like this Peterson, but again, you're rearranging the labeling of the edges completely. Here's another example here. Here's another example, and I could do a few more slides of those. There's lots of ugly looking things, which is why, you know, the more we ended up finding those things, the more we felt like, well, maybe it's a cute question. It doesn't have a nice answer. But I want to convince that you can still make sense of those siblings, at least if you make some connectivity assumption, but probably even if you don't. So let me give you an idea of what the flavor of the result I'm going to present, but I'll need a bit of a few definitions to present it formally. So I'm going to start off with a pair of siblings, and I'll assume that they're not Schi siblings, because otherwise I already know the relationship between the two through Schi's theorem. So one possible outcome is that they essentially arise from the construction, which is this K6 example. That's fine. I mean, it's a nice construction, and it's also a very concrete construction. And otherwise, I'm going to show you that we have two operations, and I can just apply one of those two operations, and then I'll get back to one class which I know, which is either that the two graphs are equivalent or that they're Schi siblings. So I'm sort of one perturbation away from being either, you know, Schi siblings or being equivalent, right? And what are those perturbations? Well, they either preserve even cycles or they preserve even cuts, right? And because they preserve even cycles, they tell you that they map siblings to siblings or siblings to equivalent graphs, for instance. So what I need to do is I need to tell you exactly what those transformations are, right? And you'll see that, well, there's two transformations, but they're really actually matrix duals of one another. So the next thing I'm going to do is to tell you about sort of very natural operations that preserve even cycles and preserve even cuts. All right, so I need to tell you about what resigning is. So by resigning, I just mean that I start with a signature here, G sigma, and then I just take the symmetric difference with that signature and the cut. And I get a new signature here, and this will preserve the set of even cycles. The next notion which I need is a notion of a blocking pair, right? So what's a blocking pair? Well, you take a pair of vertices in a sine graph, right? And you remove those two vertices there. If the resulting graph is bipartite, then it was a blocking pair. So in other words, every even cycle has to contain one of those two vertices there, right? Equivalently, you can resign it so that all the edges in the signature are incident to at least one of A or B. So that's one notion. And then the second construction, which is doing something weird, it's mapping a graph to a sine graph with a blocking pair, right? So I start off with a graph here. It has four vertices, and those dotted edges just mean that I'm going to identify this vertex there. They don't correspond to edges there. And what I do is I identify, say, the vertex 1 and 2. So those are two terminal vertices with the vertex 3 and 4. There's no other terminals, right? and I get a new graph here. And I'm also going to define the signature for that new graph by picking all the edges which were incident to 1, symmetric difference incident to 3. Right? So if 1 and 3 are not adjacent, it's just the edges incident to 1 and 3. So let me make this a little concrete. So here's a little graph here with 4 terminals. This is my graph there. And what I do is I identify as this vertex and this vertex, this vertex and this vertex there. And everything which was incident to the 2 terminals on the left are odd. I get this graph here with a blocking pair. Now that may seem like a weird thing, but it has really nice properties. And you have the following sort of this matroid dual property, which I'm going to state in terms of vector spaces. So if I look at the even cuts of the sort of folded version, the even cut of that little graph here, and I take the orthogonal space, and I get the even cycle of that folded graph here, right? So this is the relationship. So if you think in terms of matrix, it's just dual of one another. Right? So when you go from the graph to the sine graph, we call that folding. And then if you do the reverse operation, we call that unfolding. All right, so now I claim that I can use this folding operation to make very nice operation that preserves both even cycles and even cuts. And let me just go in some details on how you do it for even cuts, and then I'll just glance over how you do it for the even cycle. So I start with this graph, which has 4 terminals. It will only work for when you have 4 terminals. And then I do my folding operation, right? And then I get this graph here, which has a blocking pair. And then I do 1 flips, 2 flips, resigning, whatever you want, in whatever order you want. But the resulting graph should have a blocking pair, right? And then I resign it so that the edges are incident to that blocking pair. And then I do my reverse operation, so I unfold it. So now I get a new graph with 4 terminals. Right? What I claim is that those 2 things have the same even cuts. And it's not hard to see. This is the entire proof. So let me just go through that entire proof here. So, right, on the left, I have even cuts of GT. On the right, I have even cuts of, it should be G prime, T prime, right? And what do I have in between? Well, I did folding and unfolding, right? And so this is the folding lemma, right? So when I did this folding thing, I went for even cut to even cycle. I have to take the orthogonal space, right? And then I'll just unfold it again. So I get the second relationship. And what did I have in the middle? Well, in the middle, I just did 1 and 2 flips. 1 flips and 2 flips preserve cycles, thirdly preserves even cycles, and resigning preserves even cycles. So that's the entire argument, right? So I'm going to say that 2 graphs like this are going to be related by a T4 move. Okay, now you can see that you can probably do the same thing with even cycle, but just do the operation in the other way, right? So you start off with a blocking pair, then you unfold it, and then you do a bunch of 1 flips and 2 flips. Now you have to be a little careful on how to redefine T prime, but I'm going to skip that. And then you just fold it again, and you're going to map again even cycles of the first sine graph to the even cycle of the second sine graph. And we're going to say that those 2 sine graphs are related by a blocking pair move, right? So 2 operations, right, which preserve either even cycles or even cuts, which are really dual of one another. All right, so now I can almost tell you the main theorem, but I need to generalize this K6 construction a little bit, just a tiny bit. So I want to talk about K6 siblings. So I start off with that pair G1 and G2, which is K6 pair, right? And this is an example of siblings there. And I'm just going to allow you to make this family a little richer in a natural way. So one thing I could do is I can look at a triangle. So you can see that there's some triangles which are in G1, which are also a triangle of G2. Some triangles of G1 stops being triangles of G2, but some triangles are triangles in both G1 and G2. If this is the case, then you can just replace that triangle with an arbitrary graph. You can think of it as some kind of free sum on a triangle, which is on both graphs there. And you can just do that as many times as you want. And then if you want, you can throw away edges. Being a sibling is close enough throwing edges, except that the graph may become equivalent. All right. So now let me tell you what the theorem is. So I started with two graphs, which are siblings, and I'll assume that they're non-Xi siblings, because otherwise we already know the relationship between G1 and G2. And for now, I'm going to have this ugly condition that one of the two graphs have to be four connected, but I'll promise I'll do better after, but I'll keep that here for now. And then I need to just define a few things. So sigma 1, sigma 2 is your matching signature pairs, right? So the even cycle of G1 sigma 1 is equal to the even cycle of G2 sigma 2. And then you have this matching terminal pair. So the even cuts of G1 T1 is the even cuts of G2 T2, right? Because they're siblings. And now I'm going to, well, first assume that they're not this K6 construction. I mean, if they are, I'm sort of happy, right? That's one of the outcomes. So if they're not this K6 construction, then I'm going to pick one of those two graphs there. I can assume that it's G1. And I'm going to do one of two things. I either do one of those blocking pair moves, or I do one of those T4 moves. I do one of the two, and I just do it once. I don't string up operation. I just do them just once, right? And then I claim that what I get is a pair of graphs which are either equivalent or the Xi siblings, right? So, you know, there were all those weird constructions that we had, right? And you can make them all go away as long as you allow yourself to do those blocking pair moves or those T4 moves, right? So of course, those blocking pair moves, T4 moves are pretty powerful operation, but that's the price you pay. Otherwise, you get a lot of mess. There are lots of outcomes. Now you could say, well, do I really need this K6 sibling outcomes? You really do, because if you look at the K6, it doesn't have a blocking pair on either one of the two K6. So I can't apply the blocking pair move operation. And if I look at this K6 siblings, it has 6 terminals on both sides. So I certainly can't apply the T4 operation either, right? So somehow this is telling you, you know, the only case you cannot apply the blocking pair operation or the T4 operation is when you have this K6 construction, right? And moreover, if you're lucky enough that you can apply that operation, then in just one go, you end up with something you understand, equivalent graphs or Xi siblings. So it's surprising to me that we ended up there. In fact, I should say a little bit about the history of this. So we had looked at a version of this problem a few years ago with Irene first. We had a very complicated proof, and it didn't look anything like this particular statement. But actually, if you look at the statement, you stare at it, you realize that in fact it implies this. And then with shell 1, we essentially read the proof, and I'll give you an idea of how we read the proof in a much more straightforward way, and we were able to push it a little further. All right. So anyway, so this is the first version of the theorem here. Now, one thing which is ugly is this 4 connected condition. So we can do a little better, but not everything we want to do. We can do the following. So I don't need that the graph G1 be 4 connected. All I need is to be able to find a terminal in G1 or G2, those two things are, right? But in one of the two graphs, so that after removing that terminal, the graph is 3 connected. And you'll sort of see why, because I'll give you an idea of how the proof came about. So that's as far as we were able to push it. Now, what we really want is to prove this. So I'd like to show that all you need is just one of the two graphs be free connected. Actually, I'd be happy if, both graphs are free connected. I'd be happy with that. But we think that this is true. Now you could say, well, maybe I don't like free connectivity. Can I get rid of free connectivity altogether? I think you probably can, but then that statement, the way it's phrased exactly, doesn't work. You have to sort of squeeze in one flips and two flips in the right places to make it possible. But essentially, I think this kind of blocking pair move and those T4 move essentially allow you to reduce everything to witness theorem and to Shee's theorem without any connectivity assumption. This is what I believe. We can't prove it, right? So this is how far we got. Removing one terminal, the graph is free connected. All right. So again, what's the idea of the proof from a sort of really high level? Well, it's the same idea as what we did it for Shee's proof, right? So what you do is you pick one of the terminal, so let's say T here, and then you look at all the set edges, all the edges, say A, which are incident to that particular terminal there. And what you know is I should have an even cut here. You know that the even cuts of G1, T1 are the even cuts of G2, T2, right? And then what you do is you just delete, should have again even cut. You just delete all the edges in A here, right? And so what do you get on the left-hand side? Then you just get the cut. Because when you look at the even cuts and you delete all the edges which are incident to a terminal, you can think of that terminal as being some kind of floating terminal. So every cut becomes even. So now you know that the cuts of G1 deleted A is the even cuts of G2 deleted A T2, right? Well, now the two graphs are not equivalent, but now what you get are Shee's siblings, right? So now what you can do is you can use Shee's theorem. So you can sort of see how this kind of stuff is being built up, right? You start off with witness theorem. That's your first black box, right? And then if you want to prove Shee's theorem, you say, well, let me just pick the cut version. And then I pick a terminal on one of the sides. I just knock it out, remove all the edges. And then I get down to witness theorem. And if you want to prove the result about siblings in general, then you just remove one terminal. And then you don't reduce all the way down to witness theorem, but you reduce down to Shee's theorem. Right. So it's a very natural way of sort of building up a hierarchy. All right, and that's all. Thank you very much.
Awesome, thank you. So let's try doing applause again, everyone. So if you can unmute yourself, and then I'll count to 3, and then we'll all clap. Okay, so 1, 2, 3, clap. Not bad. All right, so does anyone have any questions? You can just go ahead and ask.
For the connectivity conditions, if you were, so I assume you're probably doing these for finding excluded minor type characterizations eventually. I guess that would be the hope. And,
that would be a nice application. Yeah.
So how do the connectivity conditions sort of mesh into what you would want to do there?
See, the thing with siblings is that it's a little awkward. I think the reason you have a lot of freedom with siblings is because you have this dual property that they represent, pairs of graphs for which you have the same even cuts in your associated graph, and pairs of graphs for which you have the same even cycles. And so, which matroid are you looking at when you're looking at siblings? There's no nice sort of natural sort of matroid connectivity to look at. So that's why I think you really want to have a version that's essentially connectivity free.
Yep.
Does anyone else have a question they'd like to ask? Maybe I'll ask one. I guess I'm not sure how to phrase my question, but I'm basically wondering about group labeled graphs, and I guess we're looking at binary and just signed graphs in this case, but yeah, I'm not sure what my question is. Like, is there anything interesting maybe about looking at if there's just more than binary, I guess, like if there's two.
Well, yeah, I mean, you could ask the same kind of question, right, with a more general group label graph. I think those questions they're very hard already here, so they probably become harder when you're trying to generalize. But you know, one thing which behaves very differently is, you know, here I just looked at pairs of graphs, right? So for instance, you could say, well, can I find, for instance, you know, 3 graphs so that, you know, for any 2 of them, I can find a signature and terminals that they have even cycles, even cuts, right? I mean, how big a set can I find? And you can't find more than 3. So 3 is the largest you can do. I think 3 or 4, I forgot, right? But it dies pretty quickly. So I think if I was to look at a more complicated case, I would say, well, can I have, you know, maybe 4 group label graphs, right, which are all somehow, you know, far apart from one another and still correspond to the same matrix.
Interesting.
Because I think that would remove a lot of the complexity that already exists at this level.
Thanks. All right, so we still have time if anyone wants to ask another question. Or maybe we'll go to an informal chat. So thank you again, Bertrand, and I'll end the recording there.